All right, so we've been talking about net ionic equations in terms of chemical reactions in aqueous solution. And so far we've talked about double replacement reactions where you have two aqueous solutions generating a precipitate. And hopefully you have some comfort level in regard to doing that. I think from what I saw from the packet, and the answers are all on Edline, you were starting to get comfortable with that, and we can look at some examples of it at the end today. We also talked about when a gas is generated from two aqueous components. For example, if you had an acid such as hydrochloric acid, you'd be looking at the proton reacting, for example, with sodium sulfide, reacting with the sulfide ion, you would generate the gas hydrogen sulfide. So that would be a case where you generate a gas from two ions, still a double replacement reaction, but you don't generate a precipitate. We also talked a little bit about acid-base reactions. With the acid-base reactions, you saw that an Arrhenius acid and Arrhenius base gives you salt and water. And you should have some comfort level in regard to titration, being able to figure out the concentration of one of the substances when given the concentration and volume of the other. And we'll be titrating in class hopefully on Monday. And it's a very good titration. I think you will enjoy it a lot. It's one of the best labs of the year. It comes early on. You titrate 2 or 3 times this year, so that'll be a good experience for you. What we're going to switch over with today are another type of reaction, and this is going to be somewhat new to you. These are redox reactions, which is short for oxidation-reduction reactions. In these types of reactions, electrons are transferred. One substance loses electrons, another substance gains electrons. And in order to understand these types of reactions, which also will be net ionic, you have to first show mastery with oxidation number. Now, this is an honors topic that should have been addressed. I'm not sure you all got it. I think most of you did. It will look familiar to you very quickly on. I had asked that you please read through the oxidation number rules. I'm not going to read through them at this point with you. I had asked you to do that. But I'll refer back to all of them as we go. And if there's anything we don't hit in the examples, then I'll be sure to go over that one so you're comfortable with it. If we look at the problems listed here, I'll refer to the rules as we go, and I'll show you how to work these. In the first example, which I'm going to put up on the screen, what is the name of this compound? Nickel 3 chloride. So the charge on nickel in this compound is what? 3 plus. If you have a binary compound, there's a couple of ways to approach this. In terms of binary compounds, if you look at Rule 7, and I'll flip screens again, it says in their binary compounds with metals, group 17 elements have an oxidation number of -1, group 16 -2, group 15 -3. So the example shown here, one of them is similar to ours. Calcium chloride, how do you know that's a binary compound? There's 2 different atoms chemically bonded together. And you have, in this case, a metal and a nonmetal. So what you're looking at here is the group 17 piece would be -1. That would be the case for a compound such as sodium fluoride, sodium chloride, potassium iodide, etc. In a binary ionic, or really any binary, not any. In a binary ionic, Group 17 piece, which will be the back piece, will be -1. Something hooking up with a group 16 as the anion will be -2. Something hooking up with nitride or any group 15 will have -3. So that's going to be its oxidation numbers. And an oxidation number is just the charge either of a monatomic ion or a hypothetical charge that you will assign to atoms in a molecule or a polyatomic.
What if hydrogen is bonded to a metal or binary compound? Would the metal have a stronger electronegativity than the hydrogen, so would it still be?
Well, the metal, in terms of the electronegativity, I think you're a little cockeyed. But if you have a metal hydride, which I think is where you're going, hydrogen typically has what oxidation number? +1. Except if you have a hydride. And in that case, the hydrogen is -1 because the cation from the metallic component is positive. So in regard to what you're looking at, who read their rules? Okay. I don't want you to memorize them at this point. Looking at the rules here, and I'm going to go through these because I wasn't aware when I told you to read it that some of you did not touch this at all. But in regard to Rule 5, which is what you're touching on, it says the oxidation number of hydrogen is +1 except when bonded to a metal. So if you have a hydride, the hydrogen will be second, the metallic component's positive.
But what if the metal has a higher electronegativity?
Doesn't matter.
Does it matter?
Doesn't matter. And if you looked at electronegativity values, hydrogen's 2.2. When we're dealing with electronegativity, I think sodium's 1. If we were dealing with electronegativity and we wanted to know those values, I think most of the metals are going to be less anyway.
So that's okay.
I mean, magnesium's 1.3, sodium's 0.9, aluminum's 1.6, manganese 1.6. So
Okay.
I don't want to say every single one because I'm not sure. Like tin's higher, 2.0. Platinum's 2.2, so that's going to match hydrogen, but I want to think they're either going to be at hydrogen or lower.
Okay, so
I don't want to say in every case, but just flying through this list pretty quickly, it looks like it is. So in regard to your question, though, the hydrogen as a hydride is -1. And let's go through some of the rules. They're not going to make sense till we walk through the example. If you have a neutral species, this is any element on the periodic table or any diatomic element or polyatomic element, the oxidation number is 0. So element on the periodic table, oxidation number is 0. The 0 piece isn't going to come in until we balance the redox reactions. Bromine, 0. Sulfur with a subscript of 8, polyatomic element, 0. If you have a compound, the sum of the oxidation numbers is 0. We'll come back to that. If you have a compound, the sum of the oxidation numbers is 0. If you have an ion, the total of the oxidation numbers is equal to the charge. So if you considered the oxidation number of H, S, and O, taking into account that you have 4 O's, the oxidation number is equal to the charge. The charge is 1 minus the oxidation number is -1. If you have phosphate ion, the phosphorus and the 4 O's together have a charge of 3 minus. Oxidation number overall is -3. A monatomic ion, regardless of whether it's cation or anion, has an oxidation number equal to its charge. So 2 minus is the charge. This has an oxidation number of -2. In their compounds, the group 1 metals have an oxidation number of +1, group 2 +2, and then aluminum +3. Let's throw some examples in there. Let's say that we had sodium chloride. So the sodium would have an oxidation number of +1. let's say that we had calcium iodide. What would the oxidation number of calcium be? +2, because it's in group 2. And this is only in a compound form. If you had calcium all by its lonesome, what would its oxidation number be? 0. Those are those free elements. And then, for example, think of a compound that has aluminum in it. Anything. Aluminum chloride. What would the aluminum be? +3. And let me give you one more just so we didn't restrict to binaries. Let's say, for example, you had aluminum phosphate. Back to Alpo. You didn't get it. The Al would be what? The aluminum +3, okay? Oxidation numbers plus or minus, then the number. Charges are number plus or minus.
I wasn't thinking of 3.
That's okay, you know how to do it. You're good.
Oh, that's what you meant by alpha.
Say what?
That's what you meant by alpha.
Alpo.
Alright.
Well, you had mentioned Alpo the other day.
Yeah, that was
In their compounds, the oxidation number of fluorine is -1. So I don't know where all my good examples went. For example, if you had, doesn't matter, sodium fluoride, you brushed your teeth this morning, right? I hope so. -1. What's another compound with fluoride?
Strontium
Strontium
fluoride.
fluoride. Is that formula written properly?
Yeah.
Really?
No.
Wait, she said that. She was like, no, you.
So what's F? -1, right? So anytime you have a compound, when is F 0? Is F ever by itself? No, it's one of those bathroom babies that needs a partner to go to the bathroom. So it's F2. It's like going on a double date. Did you ever see a girl go to the bathroom herself? Never. This was the one that you mentioned early on, Shannon. Hydrogen typically +1, except if you have a hydride. In a hydride, you have a metallic cation followed by the H. So let's look at some examples here. I did post an oxidation number video in the links thingy. All right, let's say, for example, good day. You're going to be on candid camera. Smile. Okay.
It's the iPad.
Huh?
She didn't know what you were talking
Yeah,
about.
she looked at the back of the video. She was quite confused.
That's okay. Hannah, this is for you when you're ready. It's for later. But I have to write down what time you leave, but you hold it till we're ready, because I'll leave it on my desk and forget it. In its compounds, so for example, if you had H2O, what's the hydrogen? You got it. Another compound that has H in it.
I just like cation.
Doesn't matter. Give me one, give me one, give me one.
Glucose.
Glucose. C6H12O6, and the H is +1. Oops. But if you have a hydride like sodium hydride, the H is, you got it. Ta-da! Now, raise your hand if this is coming back to you. Did you learn this last year? Were you there or there? You didn't learn it. You were there. You learned it.
I think that.
It's vague. Emily, it's in there? You were there, right? And you were there. You guys learned this. I talked to her last night. She was so excited when Andy Murray lost. She's like, are you watching tennis?
What if you had a hydride that was a hydrate also? What would the charge of H be? If because H2O.
That would be really stinky. I'm not sure a hydride also can form a hydrate, but that's a really tricky little winky. Usually when you're talking about compounds, you're not going after hydrates.
Okay.
I know what you're saying. I'm not going to give the example. I think it's going to confuse. In most compounds, oxygen's -2. However, when oxygens bind to one another, like in a peroxide, the O is -1. But you also can get all kinds of weirdness. When O hooks up with F, it's going to be positive, but you're not going to see that. So O typically is -2 unless you have a peroxide, and then it's going to be -1. So just looking back at these examples here, the O would be -2, the O would be -2. This is the rule I mentioned right away. In the binary compounds, group 17, -1, group 16, -2, group 15, -3. This is the sneaky one. In a binary compound, the more electronegative element has an oxidation number that matches its charge if it were a monatomic ion. For example, if you looked at NO, O is more electronegative than nitrogen. They do not give you electronegativity values. You need to think back to your periodic trends, your favorite. As you go across the periodic table, electronegativity increases. As you go down a group, it decreases. It's easy to remember. Say it again.
Give us that like chart.
Do we have to learn it?
We're going to get to it in great detail, the trends and all the anomalies, but here's the way you always can remember it. If you consider...
Good morning, Cobras. Teachers, please pardon the interruption. At this time, teachers, invitation only to students that received a dual enrollment pass. Please release those students down to the auditorium. Students, you must bring your pass with you. Please remember to bring your pass. Thank you.
If you consider the periodic table, what is the most electronegative element? Fluorine. The fact that that is in the upper right-hand corner of the periodic table allows you to grab that trend if you can't remember it. So as you go across, electronegativity increases. As you go down, it decreases. Fluorine's the most electronegative element, which means it pulls the bonding electrons to itself the most. Oxygen is the second most. So if you consider nitrogen monoxide, oxygen's more electronegative. What charge does an oxide ion have? If you had an oxide ion, what's its charge from group 16? 2 minus, right? So the oxidation number of oxygen here is -2. The sum of the oxidation numbers together has to be 0. So what is nitrogen in this case? Okay. And that's how we're going to work it. I'm going to throw one more example in here because this one's going to bother you. Why is that not a hydride? Why is that compound not a hydride? Nitrogen's not a metal. So if nitrogen's not a metal, what's the H? +1. So what's the N? -3. Because there's 3. I'll point that out as we go. That's going to come together. So in addition, the N is more electronegative and has a -3 oxidation number. Keep in mind as well that the H is +1 because you don't have a hydride. The rules don't make sense till you've used them. let's use them and walk through a whole bunch of this. Oh, you can do it. Alrighty, so we're going to go through our examples now. We can do it. When you watched the videos last year, could you see?
Yeah.
Yeah.
Remember there's one video that Chloe just walked
Oh my god, that's my favorite video.
All right. So nickel 3 chloride, there are a couple of different ways to approach this one. This is a binary ionic compound, and chlorine is in group 17. So what would its oxidation number be? -1. In addition, what's the charge on nickel? We said the charge was 3+. So its oxidation number is +3. The sum of the oxidation numbers has to equal 0. So you have +3 +3, I think my pen said, times -1 is equal to 0. Okay? That one's pretty straightforward. Look at this one. What's the oxidation number of oxygen? Typically -2, unless you have a peroxide. Two ways to approach this. You can look for the manganese. You have 2 O's at -2 set equal to 0. Manganese -4 is equal to 0. Manganese is equal to +4. In addition, if you name that compound, it would be manganese 4 oxide. So you could grab that as a +4 anyway. So the binaries are pretty basic. But let's look at calcium sulfate. And there are two ways to approach this. We'll walk through both. Typically, if you have a compound that has 3 different atoms in it, you're going to be in search of the middle one. You'll know what the outer ones are in most cases. Calcium is in group 2. What's its oxidation number? +2. Oxygen, group 16, typically has what oxidation number? And now you work it algebraically. You have 1 calcium at +2. You have 1 sulfur. I probably wouldn't put those ones in. And 4 oxygen at -2. And compounds are set equal to 0. So you have 2 plus sulfur minus 8 is equal to 0. Sulfur minus 6 is equal to 0. Sulfur is equal to +6. So the oxidation number of sulfur in a sulfate-containing compound is +6. And you will learn some of these as you go.
If we're solving for a polyatomic like SO4, do we set it equal to the charge of polyatomic?
That's what she said.
And here's that you can do it 2 different ways. So if you just wanted to go after the sulfate ion, which you can to find the sulfur, the difference here, you've got 1 sulfur, 4 oxygen at -2, and what do you set this equal to? -2. So sulfur minus 8 is equal to -2, sulfur is equal to +6. Okay? So this should start to look familiar for most of you. For some of you, I don't think you learned it, and it's not hard, so it's not a biggie. Let's take a look at aluminum sulfite. Aluminum in a compound is Yeah, just make it quick, because then we're gonna get into something that's just amusing. What time is it? Aluminum is +3. Oxygen. Now there's two ways to do this. You can go after the ion, which really is easier, but I'll show you both. You've got 2 aluminum at +3. This is distribution like you did in math. 3 sulfur. 3 times 3 is 9. Times the -2 for oxygen, set equal to 0. 6 plus 3s minus 18 equals 0. 3s minus 12 equals 0. 3s equals 12, and s is equal to +4. And I'll be honest, I'm writing all the steps out for you, so you've got it, but I think your math skills are at a level where you probably could have gone from here to here. But if you can't, write out all the steps. It's whatever gets you there. You've got 1 sulfur and 3 O's at -2, and you're going to set this equal to what? -2. So S is equal to +4. So regardless of how you do it, you get the same. Let's take a look at a few more. We've got ClO minus. Which oxidation number are you sure of? This is an ion. You're sure of oxygen. And this is where you really have to be careful. Now, fluorine can only be -1, but chlorine, bromine, and iodine can have multiple oxidation numbers. Oxygen is either -2 or typically -1 if you have a peroxide, but below that, sulfur, selenium, we're not going to play with tellurium, those have multiple oxidation numbers. Nitrogen and phosphorus can have multiple oxidation numbers. Carbon can have multiple oxidation numbers. They can be negative, they can be 0, they can be fractions, they can be positive. And then your transition elements also have the ability to take on multiple oxidation numbers. So this is not binary ionic, don't go there. In addition, oxygen's more electronegative, but oxygen is the one you're almost always sure of unless it hooks up with F or is a peroxide, it's -2. So we're looking for the chlorine, and what are we setting this equal to? -1 is correct, and so chlorine here is +1. That's a hypochlorite ion. Now this one also is a little funky. This is methyl fluoride, a polar covalent compound. F in a compound is always what? Good. Carbon's weird. Hydrogen in this case is +1. You've got carbon, 3 H's, 1 F, set equal to 0. You have carbon plus 3 minus 1 equals 0. Carbon here is what? -2 is correct. So carbon really has the ability to take on multiple. Try the last one. I'll do it here. It's on the screen. What'd you get? What'd you get? you get it? Yes, yes? Oxidation numbers take practice. They're not hard. I'm not going to flip you over there yet, but in your classwork packet, the B packet has oxidation number problems, as will the problems at the end of your chapter in your textbook. You do as many as you need to feel comfortable. One thing I will say,
Is it antimony metal though?
actually it's a metalloid.
Oh,
Has the ability to take on multiple oxidation numbers. It can be +5, +3. It actually can take on a lot of different ones.
okay.
I lost my train of thought.
Sorry.
That's okay. Okay, I remember now. I'm back. There are two examples here that I want to mention because you'll see them again and again in our balancing. So permanganate ion, chromate ion, and the dichromate ion. Oxygen's -2. So what's manganese? +7. That's a good one to know. You'll see it again and again and again. Chromate ion comes up a lot. The chromium here is what? You do it. You do these two. Ugh, what a mess. All right, and you got what? +6 and +6. These are going to be very helpful today. Okay? All right, what we're going to learn now is how to balance redox reactions when one substance loses electrons and the other substance gains electrons. This is a very different balancing technique. There are a lot of different methods out there. I'm going to go through with you the one that I think is the easiest and the most efficient. The packet I gave you has other methods that you can do. Whatever rocks your world is fine. Just make sure you can balance it. So with the redox reactions, oxidation indicates that one of the substances loses one or more electrons. You will see the oxidation number goes up. I'll point that out when we do it. Reduction, like the word sounds, the oxidation number is going to go down due to the gain of negatively charged electrons. And it's easy to remember, Leo the lion, loss of electrons is oxidation, says GER, gain of electrons is reduction. Those of you in AP Bio or taking or having taken AP Bio already may have learned oil rig. It's all the same thing. Loss of electrons is oxidation, gain of electrons is reduction. For every oxidation, there must be reduction. So they are complementary. They go together like macaroni and cheese. not peanut butter and jelly. The steps to balance are listed here. I'll read through these, but they're not going to click till you do it. First thing you have to do is find the oxidation numbers for the substances that can undergo changes. Figure out which is oxidized and which is reduced. Adjust the coefficient so that the number of electrons in the oxidation is equal to those in the reduction. That's the tricky wicky one. Then you're going to balance. We're dealing with reactions in aqueous solutions, so you'll very often see water as a reactant or a product. In an acidic environment, the proton will appear. It will be either a reactant or a product. In a basic solution, you'll have hydroxide ion. Knowing you have a basic solution, knowing that you have hydroxide ion signifying a basic solution is helpful. We'll balance the basic ones later in the year when we come back to this in electrochem, because the basic balancing is really tricky and it's going to be overkill. So our reactions are going to be in an acidic environment. You'll recognize them because you'll see protons. If protons are on the left, they're getting used up. If protons are on the right, they're getting made. And remember, as you have more and more protons, you're more and more acidic with a lower pH. Disproportionation reactions also are extremely challenging. I'll show you one where the same substance gets both oxidized and reduced, but it's we're not playing there. I'm going to show you how to balance these. It's already balanced for you, but I'm going to work through all the steps with you. This, at first glance, is going to look awful. Give it a chance. The kids are always extremely good at it. Okay? Years ago, all they would give you was this. Tin 2 chloride reacts with potassium permanganate in an acidic environment. And trying to predict the products is like no other type of reaction you've ever seen. I think College Board recognized that this was a ridiculous task, and so all you have to be able to do here is balance the equation. And for your lab, you'll have a redox reaction. I'll give you the reaction today. It has to be balanced before you can do the lab, or you won't know the mole ratio. So tin 2 chloride reacts with potassium permanganate. The chloride ion is a spectator ion that will not appear in the reaction. The potassium ion is a spectator ion that will not appear in the reaction. We're going to balance this equation. I'm going to rewrite it here. I will gladly, this is all going to be on film. I think that's pretty good. Or I'll scan this and throw it up. In fact, I probably can just scan the whole week's worth and throw it into one document. I'll say week of. Sound good? All right, so we're going to balance this crazy thing. We've got tin 2 ion. We have proton. We have permanganate ion reacting to form tin 4 ion, manganese 2+, and water. And now I look. I see tin ion has changed its charge. The oxidation number of this one is +2. The oxidation number of this is +4. From what we just did previously, and this is why I said this would help you, the manganese in permanganate ion is +7. The manganese ion has a 2+ charge, so its oxidation number is +2. I like to make lines. I went from +2 to +4. Did my oxidation number go up or down? Up. So did it gain electrons or lose? Careful, electrons are negative. It didn't lose, it lost, right? Okay. So what happened here is this lost how many electrons? 2. I lost 2 electrons, meaning that the tin 2 ion is the substance that got oxidized. When the oxidation number goes up, the substance loses electrons. When the oxidation number gets reduced or goes down, it gained electrons, so the permanganate ion, the whole species, is the substance that got reduced. And it gained how many electrons? 5. So manganese oxidation number changed from +7 to +2, but it is the permanganate ion that's gotten reduced. And your quiz will, on part 2, you'll have to balance one of these kooky wookies. Now, we've got step 1 and 2. I need the total number of electrons transferred to be the same. What is the least common multiple, right? Was it lowest common multiple? Lowest, you would say. Least. Least common multiple of 2 and 5? 10. What do I multiply the 2 by to get 10? 5. I want blue. I want to be in the video. Oh, I locked the drawer. Now I gotta get my pen. All right, so we're going to multiply this by 5, and we're going to multiply this by 2, so that we set them both at 10. The total number of electrons transferred is 10. When I multiplied this by 5, this is why I like the lines. I trace, I pop a 5 in, I trace, I pop a 5 in, I trace, I pop a 2 in, I trace, I pop a 2 in. And now I've got 10 electrons transferred. This takes a little practice. I'm going to show you several examples, and if you spend the time practicing, you'll be golden at this. Now I've got to balance the O's and the H's. I've got 2 times 4 is 8 O's here. And I've got 1 here. So what coefficient goes in front of the water?
8.
And now I've got 8 times 2 is 16 H's on the right. And I don't have H's anywhere except here. So my coefficient of the proton is 16. It's not so bad. Let's look at the next example. Iron 2 chloride reacts with nitric acid. Why did I break up the nitric acid on the left side of the equation? It is a
Strong acid.
It's a strong acid. That's an N. All right. Now I need you to walk me through a little bit. Which oxidation numbers in that reaction change? Iron, because this is
2 plus
+2, and this is
plus 3.
+3. Oxidation numbers plus or minus the number, those are charges. Now what?
The nitrate and the
The ends are going to change. Here, it's +5. Oxygen's more electronegative, so that's -2. So this nitrogen is +2. This is going to be a little tricky for you because you don't have a great grip on oxidation numbers yet. Had I realized that it was going to be new, I probably would have taught it last time, but what's done is done. Say it again.
Why is it plus minus?
If you had nitrate here, this is -2, n plus 3 minus 2 equals -1. Yes, yes? Yes?
So you do it based on one of the elements, not the, like, I would, like, for example, nitrate would be -1 for the oxidation number, so you do it based on the negative, not the oxygen.
You would use the oxygen if the oxygen is what was changing. Oxygen can change is if you had this at -2 and you made O2 over here, then the oxygen would be 0. You'd go after that one. The substance that's reduced is the whole substance, but the oxidation numbers for one of the elements in the substance, yes.
Wait, Dr. Taylor?
Yes,
Isn't that supposed to be equal to -1?
yes. You're right. Good job. Sloppy, sloppy. All right. We've got +2 to +3. Reduced or oxidized? Does the oxidation number go down? No, so it's not reduced, it's oxidized. Remember, electrons are negative. And how many electrons did you lose? 1. Okay, from +5 to +2 is a gain of how many? So the nitrate ion is reduced. Years ago, we used to use other terminology, which include oxidizing and reducing agents. You don't need that terminology anymore. If a problem in your book has it, don't do it. I apologize. I tried to get all those problems out. I hope I did. All right, you've got a 1 and a 3, least common multiple, 3. So what are you going to multiply this branch by? So this is kind of mathy, so it's fun, right? All right, what do we balance next? The O's and the H's, right? We're going to try not to touch those. So if I have 3 O's here, what can I put here? Don't say 3. 2, right? Because that'll make 3 O's. How many H's? 4. I'm going to do the next one with you because this one's cranky, and then you can try. All right, this one's crazy. Actually, the problem I gave on your quiz is really easy. What's changing?
Iron.
+2 to +3. Tiffany, oxidation number going up or down? Up. Oxidized or reduced? Right. You got it. Chromium. Remember dichromate and chromate, the chromium is +6. And that's why I gave you those earlier, because they're really going to stick. Now this one's weird. How many electrons does iron 2 plus lose to form iron 3 plus? Now this one's tricky. At first glance, it appears from 6 to 3 you've gained how many? However, you have a 2 here. So you have to put a 2 here, and inside in the brackets, you've actually gained 6. Go away. So these are a little trickier, and you'll see this for your lab. Least common multiple of 1 and 6? Now we've got to do the O's and the H's. We've got 7 O's here. So what goes here? What goes here? The only way you can make this trickier is sometimes you don't include the protons and waters. So if you have to put those in yourself, the key is to put the water on the side with fewer O's. The answer to the one in yellow that we did not do is on the screen, but see if you can get there. And this is a little tricky one like the previous one. Be careful with carbon. It can do weird things. And that is really what your lab's going to delve into, this type of reaction. I'll do it too. in the oxalate ion, the carbon is plus 3. Okay, so I just want to make sure you're off on the right track. Guys, I'll work it with you if you want. It does take practice. All right, so I've got it on the screen done, but I'm going to do it from scratch. It's at the very bottom. See? Yes, yes? Okay, so manganese and permanganate ion is +7, here +2. That's a gain. Don't write, just watch, of 5 electrons. So if you gain electrons, this substance is reduced. So that piece we had done previously. Do you feel good with that? Okay, then I think it got messy. In a carbonate, not a carbonate, in an oxalate ion shown here, the oxidation number of carbon is +3. And again, you will need to practice your oxidation numbers, although they always seem to give you similar ones. A lot of you had trouble grabbing this oxidation number. So if you had carbon dioxide, it's a compound, so you set it equal to 0. You're looking for carbon. You have 2 oxygen at -2 set equal to 0, and carbon is equal to +4. All right, so some of you had a few issues there. At first glance, it looks like a loss of how many? 1. But you have a 2 here. So you have to put the 2 here, and that makes it a loss of 2. Now you've got a 5-2 situation. What do you multiply them by? Each other, right? 2, 2, 2, 5, 5, 5. And 2 times 5 is 10. And then you balance the O's. and the H's. And I am going to give you a break. And you have until 5 minutes to 9 to take a short break and get a grip you could actually balance a few more. I could pick some fresh ones, or I could just pick it from your thick packet. Who's got their thick packet? I'll give you like 2 problems you should get done. This will give us about 20 minutes to break and work through. In your very thick packet, there's a whole section on oxidation numbers. So for most of you, you need to practice your oxidation numbers. This is going to be my number 10, and there are a whole bunch of problems you can work through. And then starting on page 11 is the redox equation balancing. You don't have to read through all this stuff. They show you a lot of different methods, so if you want to, knock yourself out. But on my page 17, there are some problems for you to balance, and a few of them I didn't put the protons and the water in. I can work through one of those with you if you would like. But if I were you, I would try in the next 20 minutes to balance 1, 2, and 4. And that would be very good for you. But I would take a break first.
What other pages did you say? Was it just on
First 10 and 17 if you want to do that.
Yeah, 10 is oxidation numbers. I wouldn't play with that now, that I would play with over the weekend. But on page 17, I would try and do 1, 2, and 4, because you'll feel a little bit better once you start to balance these. It takes practice. And then I'm going to let the videotape continue to roll, because if I turn it off, I've got to upload twice. So just during your break, keep in mind that it's on. Question? Yes.
How did you get like the changes? Why did you give so many?
Because the least common multiple of 2 and 5 is 10, so I have to multiply them each by the factor that will make it 10.
But why did you like put 5
The 5, if you follow the train, the 5 pops here. The reason why a 5 didn't go there is because it had a 2 there, and I had to multiply it by 5, which made 10. All right? And one of those problems I recommended is like that. Yes.
I found an exam last year with AP balance questions and multiple choice. I got like a review book and I opened it and like the
All right, guys, do those 3 problems. Go. Sometimes they are the same. It just works that way sometimes.
Would this have like a minus 1 charge?
Yes,
Even though it's by itself?
but it has a charge on it. So if you have a monatomic ion, the oxidation number is the charge. So this would be +1. This is 0. You've got it.
Okay.
Yeah.
Do we like basically never touch the H's?
What do you mean? Never?
Like,
Not, you don't
You don't
usually go
usually do.
after the H's, but you can, like if you made
Okay.
hydrogen gas. So there are some single replacement reactions which will hit where you can go after that.
What exactly is, like, is manganese literally losing electrons, I'm sorry, yeah, losing electrons, or is there, like, is it just happening through, like, the O being separated from it? And I feel like it's
It's not separated. The substance that was produced is the permanganate ion.
right.
In the permanganate ion, manganese undergoes a change in oxidation number from +7 to +2. That's the terminal.
But like in terms of the reaction, what would happen? Like if I were to do that reaction, what would actually happen to manganese? Like would it?
You're generating a new substance with a different
It's just
oxidation number.
Okay.
This one? This is,
those review books until like
I would get them now.
because
like-
mine came in.
Right, and so the stoichiometry stuff, you can
It's
do
in
those
there?
multiple choice. If you can't find something, show it to me. I'll help you.
Okay.
So for the review books, you want us to work on it throughout the year?
Yeah, get it now.
Because I got it.
Yeah, your sister's probably too old, even though it was the new course, they bettered it.
I got the 2017.
And that's where I would have gone.
So I was just talking for college applications. Do you still believe in your child? You saw me trying to bring that for chemistry.
Did you take the bio? You might be better off taking the bio. What field are you going into? Bio. You can bio, because you already have the AP under your belt. And the kids said the biology. The chemistry one, I mean,
Yeah, it would take longer to
well, there's just too many pieces I think are missing. But take a look at it online and see if you think we can fill in a few blanks and you can go.
Can you sign? You can just like draw the arrow down if you want.
What do you got, Chip?
Oh wait, never mind. I figured it out.
Oh wait, can you check the first one?
Hazel.
I didn't finish this one.
That's right, you've got the pieces right. The kids practice.
Like that.
And the least one is 6. So we must have okay, so those go to 3, right?
But they could be two because they're
Yeah.
yeah, right? Yeah. Okay. So that makes sense. And then the rest of it is all
It's like, yeah, it's all nice. That's the new one. So this is zero.
like when you multiply and things to them.
Yeah, so that's a one electron. But then you have to change it to two because that's the two subscripts.
Okay, you think of the
Add
power.
two electrons.
So you divide them by 5. So you don't have to don't miss the other.
What did I do? Please tell me.
You don't want that. Does that make sense? And then you balance the O's.
So,
There's 4. That's right. 2. That's right.
yeah.
That doesn't balance. Now you just balance the H's and the O's.
So what am I supposed to do?
Yeah.
What am I doing wrong?
Well, because you got that number, which that would just be a 1.
So you got those.
Because it's already balanced. Okay.
So this is
6. So see, this would be
Just, why would that be a six?
because there's 2.
That'd be two, 'cause that would be two.
And then this one's B3. And that one B3.
Yeah.
And then you have to balance it.
Nice.
Did you get that one?
Nice.
Yeah, and then it ruins every.
Yeah. I'm gonna look over this one extra special.
You just
for
go
you.
too fast.
You check too.
Yeah, basically.
You don't think
Unless you don't want to go
before you write.
That one's right. So this one has to be a two and this one one.
6, so you can multiply this by 3.
Right, Mom?
16.
I write it down.
That's a two and that's a one, cause that is a two, six, three.
There you go.
Yeah, there you go.
There you go.
Use that mouse. Balance. That's a one and a one.
7,
Damn,
and
I'm
then
doing good now.
16.
Oh, yeah, and 12, that's right. And 8.
No, PR is
So,
two.
just 6 practice, you're getting it. Put that there, that's going to be 2, right? Loss of 2.
Oh.
I thought you
Oh, because there's two. Okay.
Right, and then that's a 2 that, well, not completely, because you had the, yeah, then you started throwing 2s. Yeah.
Or you can just think you're on the same.
All right, there is one more type of redox reaction that's much, much easier and you've seen before I want to show you. And I've just been going through to figure out how we can make this all work. And I'll explain it at the end. But there's one more type of redox reaction I want to show you. It's much, much easier. So the worst is over and the easier stuff is coming. If you want to stay over at the lab tables, that's fine, but you have to be able to see the board and pay attention. And at the very end, I'll either write down everything that you should be working on for the weekend, or I can send it as a remind, which I think most of you would prefer, right? Because then you have it. Years ago, we used to use terminology like oxidizing and reducing agents. You are not responsible for that terminology anymore. It's a little bit of a shame because it's what you see on bottles of chemicals, but we'll let it go. So this section here, 5, we're just going to let it go. There are some tricks in oxidation numbers in number 1 that you may want to just read through. But what I want to focus on are single replacement reactions, and these are redox reactions as well, and you're familiar with writing them at a molecular level type equation, but writing the net ionic equation will take a little practice, and this is in your POGL packet. So after this, you should be able to work through the rest of that. Metals actually get oxidized in single replacement reactions. And you've seen activity series of metals previously. You would be given an activity series. And how do you read that activity series? The most or the greatest activity is at the top. That's exactly right. So lithium can displace anything below it. Rubidium can displace anything below it, but not lithium. And the weakling is gold. It doesn't have the ability to displace any of the metals, including hydrogen, above it. So last year, what you would have seen is something like this. Magnesium reacts with with a solution of copper 2 chloride. And you would be able to write this. You'd say, ooh, magnesium will bump out the copper component, generating copper, new compound, correctly formula written. This year, what we want to be able to do is write a net ionic equation, and we've been through net ionics, so I think you'll be good here. This says aqueous, which means you break it up into the ions. This is aqueous, you break it up into the ions. The spectator ions are chloride ions, so they cancel, and you have your net ionic equation. And take a good look at that. You have a metal reacting with an ion. The metal generates its ionic form. The ionic form gets changed into its solid form. And you may not recognize that as such, but it really is a redox reaction, because you have magnesium by itself reacting with copper 2 ion to generate magnesium ion and copper. So you're going from 0 to +2. This is a loss of 2 electrons, and you're going from +2 to 0. So this is a gain of 2 electrons. Okay? So pretty straightforward here in regard to redox. The substance that gets oxidized is what? Which substance gets oxidized? Magnesium, because it loses, and the copper 2 ion gets reduced. So magnesium reacts with copper 2 ion. Why can't copper react with magnesium ion?
Copper has a little charge, magnesium can.
Because copper has a lower activity, so copper doesn't have the ability. So these reactions only run in the forward direction. They are not reversible. Okay? So if you had this, you'd have no reaction. So let's try and balance a few of these. We'll do the first one together. It says calcium reacts with a solution of zinc chloride. We want to write net ionic balanced equations. Now, I'm not sure if you'll be able to jump to the end right away or if it'll take a little bit of working through it. We can try it both ways. So in A, we've got calcium reacting with zinc chloride. In a single replacement reaction with a metal, I'm not sure. Can you go to this point right away? You can work through it, it's fine. You could do calcium chloride and zinc, and then the chlorides are going to cancel. That's a Z. Don't worry about balancing it till the end, it's not worth it. And so you ultimately get to this. Why is B no reaction? Because cadmium's below sodium. Good. So how do we do C? It says sodium reacts with cadmium bromide. How do we write the net ionic for that one? What do we do? What do we do? we'd have sodium. It's going to react with the cation, which is what? Cadmium. What's its charge? Always 2 plus. That is like zinc, which is always 2 plus. And what do you make? Sodium. You can do sodium bromide. And cadmium gets pushed, right? So the bromide cancels. What ion do you get from the sodium bromide? Why is it 1 positive? Because it's in group 1. And cadmium. Is that balanced? Why not? So if that's 2 plus, you need 2 pluses on this side. So you need 2 sodium ion, 2 sodium. Try this one. What'd you get? Magnesium plus what? Aluminum ion, right? What ion is generated? With what charge? And? Is that balanced? Now look. You have 3 plus and 2 plus, so be careful there. 2, 3 makes 6 plus on each side, correct? 2, 3. Now if you want to walk through every step and let it rip, that's fine. In a single replacement reaction, Hannah, I'm going to hit your question in a sec. When you have a metal, it'll react with the cation, so the anion will be the spectator.
This is probably a dumb question.
No dumb questions, don't worry.
How do you find out like what's create like the products?
This just goes back to your single replacement. So this piece gets bumped, so you know it's aluminum, and then you make the new product that you have formula written correctly. And in these single replacement reactions, what will always cancel out if you have a metal is the anion will be the spectator.
Why doesn't aluminum have a charge?
Here, when it gets bumped out, it's all by itself. It's not an ion.
Okay.
And what's the oxidation number of aluminum? 0. Okay? The other 2 examples here I will show you. They're slightly different, but it's stuff you also saw in honors. It says metals are oxidized when they react with acids. So in the example I gave you, and it's all written out, it says aluminum reacts with hydrochloric acid. Hydrogen, of course, is not a metal, but in this activity series, it almost reacts like one. Aluminum has greater activity than hydrogen, so it will bump it. And the only thing you have to be careful with here, what compound do you form? Aluminum chloride. And now when the H gets bumped, usually things get bumped as metals, but H, of course, is not a metal. It's a gas, and it's a diatomic gas. So when hydrogen gets the boot, it's like this, but the net ionic is still the same derivation we've been dealing with. Cation, cation, hydrogen, gas. And this one too is a bit of a mess to balance, and the balancing just takes practice. There was another one here too. It said magnesium reacts with nitric acid. So what are we going to do? Kick out the hydrogen as what? Good. And what's here? You can do magnesium ions. Some of you may prefer to do this. Then you're going to have magnesium reacting with what? Proton, generating, and I was going to call you Chloe, but that's not your name. Sydney, go ahead.
I forget my question.
I'm sorry.
Oh no, it's okay. No, I just came back. I lost it.
This usually happens when you get older. Just jot it down.
Getting old.
No, I'm saying
Oh,
you're,
okay.
okay, it's back.
Why did you have to put a 3 when you were balancing? Why can't you just put a 2 in front of hydrogen? On the left side. You put it,
Here?
yeah. I feel like that's really stupid of me to ask.
No, I know what you're saying. So we had this. And you initially wanted to do this, right? Correct?
No, I wanted to just put the 2 there.
You wanted to put a 2 here?
Yeah.
Okay. Then you have 2 pluses here and 3 pluses here, right? So that's not balanced for charge. So what would you multiply this by and this by?
Balance the charge.
Right, so when you multiplied by 3 here, you got 6, and when you multiplied by 2 here, you had 2, and then 3 to balance the H's, and the 2 to balance the aluminum. Alright? Alright, I'm going to cut.
Mrs. Ario?
You have the wrong classroom.
Okay, thank you.
Alright, we have 5 minutes. We have some stuff to figure out.
Can you push down?
Yes, well, yeah. Yeah. All right, couple things to figure out. Well, I'll put it back up. I don't want the bell to ring because I've got to show you where we're at. All this oxidizing power, I'm going to cut this off. Bye-bye.